Well, let's get started. And someone commented in the chat room, there is a new assignment. And I need to give my warning. Whenever I give an assignment involving the visitor pattern, students want to optimize it away. So one reason there's, you have to implement two visitors that return different things is hopefully to avoid that from happening. Are there any questions? Well, we're almost done with all the patterns from the Gang of Four book. And then we'll move on to some other patterns. Depending on how much time we have, we also will look at some different architectural patterns. The patterns in the Gang of Four book don't tell us how to structure applications. And there are a number of patterns where talk about how do we structure applications. So last time we were talking about memento. So today I want to start looking at the mediator and go on to facade and some other patterns. So let me share my screen. And then go through the ritual of rearranging screens. And now I need chat. Okay, the patterns that I talk about at the end of the Gang of Four text are the ones that I put off to the end for a reason. Some of them are hard to talk about in terms of they're not used much, or you may not have experience to deal with them. The mediator is one of these. Now, so the goal is control and coordinate interactions between a group of objects. So instead of having, as we do here, a bunch of objects interacting directly, we then have the communication go through, a central location, a mediator. The structure is pretty simple. We have a mediator interface. They call it a colleague interface. Those are just the objects that we interact with. And then the concrete mediator has reference to all those they call colleagues. And right, the mediator finds an interface or how the colleagues are going to communicate with each other. Concrete mediators that API. All the colleagues know about the mediator, but each colleague doesn't know about the other colleagues. So the one example I have to try to motivate this is, you have some sort of dialog box. It has, you know, a list box and a button, various fields, and there may be a relationship between them. So when you pick one option, other options go away or other options appear. Right, and so the director, you know, so maybe you pick an option in a list, and that means other options have to pop up. So instead of having that list have to know about this other option over here, it just tells the mediator, look, okay, they've selected item 3, and the mediator then is going to tell another entry, oh, item 3 was selected, so show the sub items related to item 3. So anyone want to take a guess at this?
To me, I think mediator doesn't do any of the work. I guess it keeps its boundaries. Its only job is, I guess, directing or managing the colleagues without overstepping its boundaries and scope.
Yeah, that's exactly right. The mediator, you know, it's like a director, right? I mean, you do the, you know, this happened, you do something, right? This happened, you do something, as opposed to, oh, I'm going to, you know, item 3 was selected over here, so I'm not going to populate this list over here. No, the other list will populate itself, right? You know, and here's why, this is one of the patterns I postponed to the end, right? When a set of objects communicate in a well-defined but complex ways, you know, what does that mean exactly? You know, the second one is a bit more easier to understand. I mean, if you interact with too many things, it can be hard to reuse because it interact with them, you're going to have to pull them with it. Well, but if you not only interact with a mediator, it's going to be easier to reuse. Right, and the third one I think is also a little bit easier to think about, in that the mediator is going to grab some responsibility from multiple classes. So now if you want to change the mediator, you can in one spot as opposed to having to change all the subclasses. So this is the font selector from Visual Smalltalk. So every time you make a selection here, other things change. So if we, you know, select items in this list, that's going to change what fonts are listed here. And when I select this font there, it's going to show us, right, the current value, the new value they look like. And also different fonts have different sizes available. So all these lists are intertwined. And when we build this particular dialog box, each of these components are just our lists, our text inputs, buttons. Slightly simpler. Again, for example, here's a sort of a fake implementation of in buttons, right? The OK button has to worry about, okay, have you enter any text? If you enter text in both of them, then we can check them to see whether they're valid and go on. The mediator, we can then bring, now worry about subclassing buttons, so we can now put together a dialog box to handle some of the logic in the mediator. Right, so instead of creating special buttons, there's no special buttons, and the mediator gets notified when the OK button is selected, and then interacts with different colleagues to get work done. So far, so good. Is it clear why this is one of the patterns I postponed to the end? Yeah, again, as time moves on, we find new constructs. So reactive X can sometimes reduce the mediator just doing streams of processing data. So that's one change since the text was printed. The facade is another one that I postponed to the end. And here, scale matters. So, I probably told this class already, but once came across an article with programmer was explaining, well, when I was in school, right, there was a sort of, you could write programs up to about 2,000 lines of code, and after that, it just got too complicated and it's hard to deal with. So I had to learn to go beyond that. He had to learn different ways of putting the code together. And so once they did that, he then ran into another barrier, about 10,000 lines for a particular project. Right? And again, he had to reorganize his thinking, how we organize code, right? And each time he'd still come across a barrier because, once the projects got larger and larger, you had to use different techniques to deal with that scale, right? So one of the problems we have, talking about some of these patterns is that we don't need those patterns for small things, right? And the assignments I give in this class probably would be better off not using patterns. But the goal of the assignments is to get you to, use the patterns to get a better understanding of how they work. The facade is one of the patterns dealing with scale. And to understand what we mean by scale, I have this chart. For some of these things, it's hard to find that, good information. Yeah, this is an old US jet fighter. It has like 1.7 million lines of code in it. The Boeing 787 has about between 6 and 7 million lines of code in it. The Chevy Volt, which is no longer in production, had about 10 million lines of code embedded in it. And again, this information is old. This is before cars was trying to be self-driving or semi-self-smart driving. Just the radio and the navigation system, right? The GPS system, those two things, just those two things have 20 million lines of code. And again, this is probably 10 years old. An earlier version of Mac OS 10 had like 86 million lines of code. New automobiles, usually about 100,000. This is before we have self-driving features. Debian 5 has like 350 million lines of code. Tesla is built on top of Linux, right? So they don't tell us, but this is a lot. We're probably north of 500 million lines of code, right? That's for a car. And for comparison, the text has about 8,000 lines of code. 8,000 lines, right? So if we were to print out one of these programs, the Boeing 787 would probably have about 100 textbooks the size of design patterns book to show source code. So the facade pattern is one which they use to help deal with larger systems. So the idea is that you're going to create various subsystems, and then isolate that particular subsystem or set of subsystems. Clients interact with the facade, which will pass it on to the subsystem. Right, so the clients don't have to know what's going on behind the facade. It appears to be one system instead of a bunch of different classes. So in essence, right, we build classes, right, to hide details and information of the class, so we don't have to worry about it. Facade basically is scaled up so we can hide detail of the systems in a facade. So facade is like a scaled up version of a class. Now, I suspect that no one in the class has dealt with systems and a million plus lines of code, right? Anyone? Lonzo, so you've worked on systems at large?
I've worked on them, but our at work, our system, we use plugins, so I don't have to like touch that, but I have to look at it all the time. So I know our code base is bigger than that, at least, but I don't have to make modifications to it.
Yeah, and most of the details of that source code is hidden from you, right? You don't have to deal with it. You can look up an API and it's the same thing we do with classes, right? We want to hide that information so you can forget the fact that there's a million lines of code behind you, in front of you. You're just like, wait, I just have to worry about, here's my API, I use it, I'm done, right? And that's basically what the facade is trying to do, is, take, so the navigation subsystem and convert it into one class to interact with and get things done when you need to get done. Right, like I said, the whole point is to hide how the subsystem is implemented. Clients have to worry about it. And again, it's going to allow us to change that subsystem without clients knowing what the changes. Exactly what we talked about in class. It's sort of hard to prevent clients from talking directly to subsystem classes, depending on your language. Text sort of hints that you might need to do that. But it's probably much better if the clients never talk to the subsystem, just talk to the site directly. Yeah, again, I talk about making public and private classes. But again, it's probably best to put as many as possible private, so we don't clients don't know about them. One example that I know about the facade pattern is compile and visual Smalltalk. One difference between Smalltalk and most other languages is that the compiler is written in Smalltalk, which is not that uncommon. But what is uncommon is that the compiler source code comes with Smalltalk, so you can see the compiler, and at runtime, your code has access to the compiler. But you only interact with the compiler class, and you do things like this. You compile it, evaluate, and give it a piece of code to evaluate. There's still all the parsing going on behind the scenes, building up that syntax tree, code generation, all that's still happening. And it takes a lot of classes and a lot of code to do that for a general program, but they provide this compiler class to hide all that from the programmer. So you just call compile evaluate. And there are a number of methods you can call. So you can actually at runtime call the compiler to have it do things for you and have no idea about any other class besides the compiler. And we have one student who knows what that means, right? All the work you need to do to get a compiler working. It's usually a semester-long project to implement a small compiler. And a one side fact that's sort of interesting. Donald Knuth, when he was a student, he used to write compilers on the side to make money on weekends. He was very good and fast at it. Here's, creating a method and then compiling it at runtime. And just an example of using facade where all you know about is the compiler. Objective-C, they have what they call class clusters. So when you need to wrap a number of various types, an object to go into in an array like you do in Java, you just use number, and it's a facade for all the other ones, and it will do the right thing for wrapping various text objects. It's not as good an example of facade as the compiler, but nonetheless. So any questions about facade, mediator? No. I guess you guys didn't get the espresso coffee I sent. Okay, so let's go on to the last Gang of 4 pattern, the flyweight. So, one issue that people usually don't talk about is there's a fair amount of overhead for objects. I think in Java, an object that has no fields still takes like 16 bytes. And then when you add fields, you add more data, but you get 16 byte, I think it's 16 bytes, not more overhead for each Java object. So if you're going to create a lot of objects of the same type, and each object doesn't hold much data, most of your memory consumption is the overhead for the objects, not the actual data. So the question is, right, so the flyweight pattern is designed for that situation where a large number of really small objects how can we do that efficiently? If you got 10,000 objects in Java, that's a lot of overhead. And if each object only holds one integer, it's a lot of memory consumed by just object overhead. So the example the text uses, I use, if you're going to build a word processor with objects, and you're using characters as objects, there's a lot of information that the character needs, right? The font just is the width, the height, the font size. Is it have ascenders, descenders? Is it bold? Is it all this information? And most of the time, right, when you have character A, it's the same font, the same width, the same height, all information is mainly the same. Some of them might be different occasionally, but if all that information for an A is the same, then we can use the same object for A, and whenever we need A, we just point to the same A object, right? And Java does try and use a system for strings to minimize space usage. So let's look at the first set of comparisons here. Define a string called cat rat. Another one just contains cat. And now when I take cat and combine it with rat, right, and compare it to the string 1, it turns out it's false. They're not the same. They're not equal. And the idea why?
Are we comparing the identity of the object and not the string?
Right. Equals in Java just compares whether they point to the same object. Now, if I take A2 and combine rat and intern it, now I'll compare the result to A1. They are equal. So what Java does here, whenever we have a string literal like this, it keeps it around, and if it sees another string literal equal to it, it returns, it doesn't have 2 copies of it, only has 1 copy. And if you call intern on a string, it's going to add that string to the list of strings it's going to look for, and always return a canonical copy of that string rather than allow you to create multiple copies. So when we take this string and say intern, intern is going to look at the list of existing strings it knows about. It finds one with the same characters, and it returns the string it already knows about. So that's why A1 and A3 are identical here, because they are actually pointing to the same object. With string 4, what's going on is the compiler is combining cat and rat. So that is still a string literal. So it goes into the intern pool. Right, so what Java is doing is keeping this intern pool canonical representation of the same string. So if it appears multiple times, we're not creating duplicate strings. We're actually always getting a reference to the same string over and over again. Is that clear what's going on here? So that's sort of an example of the fly rate, right?
Wait, sorry. Just to make sure, in the previous example, for the last two asserts,
right.
are those are false?
No, those are equal.
So what is the so how come in A3 we had to use the intern function?
Yes, and this is what confuses beginning Java programmers. Okay, in A4, what's happening is the compiler is performing a plus operation because it's an assignment statement to a new variable. Right? So the compiler does it. And it would not do it when I assign a string 3 because it's not two literals combined, right? It's a variable plus a literal. And so the compiler is not going to, at compile time, kind of figure out what the contents of that variable are going to be, because since the variable, the contents could change, right?
Okay, that makes sense. All right. Sorry.
But it is confusing because, particularly for beginning programmers, sometimes strings are equal and sometimes they're not equal. And most reading textbooks do not talk about interning strings.
I mean, normally you would just use like the dot equals thing, right?
Right. But the equals equals is going to be much, much faster. And the goal here is to show an example of the fly rate. So the fly rate pattern, I talk about intrinsic and extrinsic state. Intrinsic state is information that's independent of the object context. And so that information can be shared among many objects. So that information we can put in fly weights. Extrinsic state is, depending on the context, so we can't put it in the fly weights. So the goal is we gather we have a large set of what they call fine-grained objects. We're going to pull out all the intrinsic state and put it in one object, and all that intrinsic state we have to store somewhere else. Let me skip a few slides and look at a simple example. Okay, run arrays. So if I've got this sequence of characters, right, it's going to be cheaper to store this information in two arrays. And now only need arrays of size 3. Right, so the first array contains the characters, and the second array contains the number of times that letter repeats. And so now, right, so this, the top list is going to have 26 characters, whereas the bottom array is going to have 3 characters and 3 integers, right? So when we get data which has lots of repeating values, it usually can be cheaper to store it in a run array. So far, so good. Right, now let's say we had the first chapter of the first and second chapter of the book, a given example of the Select document editor. They had character objects, and character objects need to know their font information. And so if we're going to store, right, this particular string using separate characters, and the font information is almost always the same. So we could use run arrays to store extrinsic state. Again, I just need, right, is a normal font for the first 22 characters. It's 4 characters of bold, and then 18 characters normal again. All right. So I can pull all that font information out, and then just store, in some sense, just the ASCII characters here instead of storing all that font information. I can pull that font information out.
So would we want like a run array for a whole bunch of like different font informations? Like we could have like uppercase like 3 and then lowercase everything else, and like stuff like that, if there's like multiple different factors that you could have.
Well, uppercase and lowercase are different characters, right?
But for example, if we had like italics in there as well, or
yeah. And so here I'm just worrying about, bold or not, but normally what we store here is the font information, right? The font size, right? What the font it is, etc. But in most documents, how often do you change that? Right? Usually the paragraphs all the same font, right? And occasionally you might have italic or bold. And then you can have headers, which are usually a different size font. If we get a textbook, right, for the pages and pages where there's very few font changes. And so rather than repeating that font information for each character, you'll say the significant space, right, by pulling all the font information out in a run array like this, and then just store the ASCII characters in the actual character object. So far, so good. Now the issue is, okay, so in this document editor, right, we're going to use objects for each character. We're going to pull out all the extrinsic state in a separate location in there, right? But still, when we're going to render, this line of text or the paragraphs or whatever on the screen, we need all the information, right? You need to know what font it is, what size it is, if it's bold or not. So we need to use those objects. We need to go find the extrinsic state and combine it with intrinsic state when we need it, right? Does that make sense? If we're pulling the data from one object into two pieces, one over here and one here, when it comes time to actually use the object, we need to pull the information back, right? So we have all one when we need it. And that is when we look at the fly weight, there's an operation called a method called operation, and you pass in the extrinsic state, right? So when we go and render that, the text, when we go to the flyweight object, which represents the A character, we need to give the A character, right, the extrinsic state that it needs. Here's your font, here's your size, whether it's bold or not. Does that make sense? We also need, right, the flyweight factory. An example of the characters in the Word document. Every time we want a new character, we want to use the same flyweight, right, as we can to save space. And so we need some way of saying, give me an A, give me a B. Just like when it's in Java's intern, right, there's a factory there which stores all the intern strings. So hopefully it's clear. Why is another pattern I postponed to the end. Is not, the situation is not something you'd like to come in contact with. Right, so the hard part of this pattern is, separating the state Yeah. Right. Identifying the Trinity state with we have to pull up with the state we can pull out. And making sure that we actually save space by doing this. Any questions? Okay, something slightly different. So a number of years ago, there was this project in the university called Demeter, and they noticed something that helped produce better code, and so it became known as the law of Demeter. And the formal definition is slightly obtuse. So you've got an object O, any method in that object can only call methods on O. That makes sense. If you're a method in a class, you should be able to call methods in that same class. And again, that method has arguments. You should be able to interact with those arguments, right? Call methods on the arguments. If the method creates objects, we should be able to call operations on those methods. If O has fields and those fields are objects, we should be able to call methods on those fields, those objects. And global variables. That's it. Now the question is, what does this exclude? So another way to rephrase the law is use only one dot. I'm just calling a method on an object I know about, and that's okay. This is not okay by the law of Demeter. Why? Because what's B? It's not the object we're in, right? It's not a field of the object we're in. It's not an object we created. It's something inside of A. So why not allow this? Do we know the type of B? Yeah, reduces coupling, right? Now if we go back here, right? If I'm in O, I know the type of O, that makes sense. I know the type of, in Java, types of arguments of M we know because that's part of the declaration. If I create something inside the method, I know its type because I created it, right? And any field in that class, we know its type because we declared it in that class, right? And if it's a global variable, then presumably we know that too. But when we come to here, we don't know what B is, right? That's one problem. Second problem is, what happens if we want to change the internal structure of A? Well, now, right, we're coupled to the fact that B has to be inside of A, right? Because all of a sudden it reduces coupling, right? Because this is now, we're coupled to the internal workings of A. And this one isn't quite as bad. We're no longer necessarily coupled to the internal workings, the structure of A, but we still don't know what does B return, right? Given allowed meter, we didn't, it's not an argument, right? It's not a field that the class we're in. It's not something we created. We do this, right? At least we know what type foo is going to be if we're in Java, right? So the coupling there is explicit. But it's still just a long way of doing two dots. Right? Foo is not something we created, right? It's not something, it's not an argument for our method we're in, it's not a field we're in. So how do we what if we need to do that? What do we do? Boy, you're lucky we're not meeting in face to face. We couldn't answer this question. They pull out my stick and start beating people over the head. Before we had, projectors in all classrooms. They used to carry a stick to class, right? So I could beat you over the head. So I go back to Dilbert here, right? What are we doing? We're saying, well, I need some information. I need this thing inside of A. I need and rather than telling A, go do it yourself, you do it. I'm saying, you know, go do this, and then I'll take the result. I'll do half of your work. So the way to replace, you know, this construct would be to ask, just send method C to A and have A do the work completely for us, rather than pulling things out of A to get work done. I remember the Dilbert cartoon everyone was puzzled about, where you wanted to always have, you know, push off work to others that you can push off and only do what you have to do. So basically, we're saying in all these cases, okay, let A do part of the work, and then I'll do the rest of the work, rather than saying, oh, A, just do everything for me. This one person is looking a little puzzled. Have a slight pause, see if anyone questions. So what about the builder example, right? Does this violate the law of the meter?
Well, it doesn't necessarily, but it does mirror those last two examples.
Right. The difference is, right, that I am building the object here, right? I'm creating a new notification, and then I'm sending multiple messages sequentially to that particular object. So I am, right, only send a message to an object I created in this code, this method, which is allowed in the law of the meter. But I am using multiple dots so that that rule of thumb is rule of thumb, right? Only one dot. Difference here is I am sending the same message to things, the same thing which I created here. So this really doesn't, right, violate, oops. No. Right, each method returns a builder, so we're looking at calling methods on things we created. You know, so we could do it this way, right? I mean, we're basically creating the object and then sending messages. But this is, I think, a lot harder to read.
Well, couldn't you have done that in the second bad example you showed, where you were running a function or a method call, and then you're running a method call on that the return value of that?
Well, but remember, I'm creating the object here, right? And so law of the meter says, we go back, I can send methods to objects created in the method, right? So when I go to, these examples, right? I'm not creating B here. B already exists in A, right? In general, we don't know what method B is doing, right? Um, and the reading list, I gave a link to an article that talks about log meter, and it talks about slightly differently, not this formal way of, right? It doesn't use this formal way of talking about log meter. Any questions about the law of the meter? No questions. Did I forget to tell the class that the person who asks the most questions over the semester gets an extra 5 points? Tough crowd. You can hard to get a reaction from these guys.
My answer would be, did you?
You're the one listening. You should know, right? Well, I don't know if it'll happen, but we have, by the end of the month, we have to put together the fall schedule. And it'll be months after that before we can see it. But the college is assuming that we'll be face-to-face in the fall. So then I can bring my big stick. Maybe bring some espresso coffee, right, to class. Hopefully that happens. I think we're all tired of being in Zoom in our own rooms all day long. So we're almost out of time. I think I'll stop here. I have a slight audio problem I want to try and debug before my next class. So,
Thank you. Have a good night.
Thank you.